Show that the function f of x equals x cubed plus 4 over x squared plus 7 had exactly 1, 0 in the interval negative infinity to 0. To show that there is exactly 1, 0, there are two things we need to show. One, we need to show that there exists one, so this is the existence, and two, we need to show that it is unique, and so this is the uniqueness. To show that there exists one, we will use the intermediate value theorem, and to show that the solution is unique, we would use the Rolle's theorem. To use the intermediate value theorem, we first notice that this function is continuous on the interval negative infinity to 0. As of now, it is not continued at x equals 0, but 0 is not in this domain. And so, it is continuous on the interval negative infinity to 0, and it is also differentiable. But we only need continuity for the intermediate value theorem. To show that there exists a 0 or a solution on any interval AB, we need to find one positive value and one negative value of the function. In this case, we were not given such intervals, so we would have to find one. Just pick any value and test it to see if this works. For example, if x is negative 1, then we have f of negative 1 equals negative 1 cubed plus 4 over negative 1 squared plus 7. And this is negative 1 plus 4 plus 7, which is a positive number for sure. We use a negative number because the restricted domain is from negative infinity to 0. Next, we use x equals negative 2, for example. F of negative 2 is negative 2 cubed plus 4 over negative 2 squared plus 7, which is negative 8 plus 4 over 4 plus 7. And this is negative 8 plus 1 plus 7, which is 0. In fact, x equals negative 2 is the solution in this case, but to use the intermediate value theorem, we insist that we need to have one positive and one negative, and x equals negative 2 wouldn't give us a negative y value, so we would have to pick another one, x equals negative 3. F of negative 3 is negative 3 cubed plus 4 over negative 3 squared plus 7. This is minus 27. 3 times 3 times 3 plus 4 over 9 plus 7. And we see that negative 27 plus 7 is negative 20. Negative 20 plus 4 over 7 is negative for sure. Remember, we don't need to know the exact value. All we need is just one negative and one positive y value for the intermediate value theorem to work. We have everything we need to write the intermediate value theorem. We say that f is continuous on the interval negative 3 to negative 1. That is the interval that we pick because it gives us one negative and one positive. We have f of negative 3 being a negative number and f of negative 1 being a positive number. If at negative 3 we have a negative y value and at x equals negative 1 we have a positive x value, then at some point the function needs to cross the x-axis, and that x-intercept is the solution. But to finish this, we will say that since f of negative 3 is less than 0 and 0 is less than f of negative 1, by the intermediate value theorem, there exists, this is the existence proof, and x equals c such that f of c equals 0, and we say that this is a solution. And so we show that there exists one. We just established the existence of such a solution. There is an x equals c, the solution, such that f of c equals 0. Now we need to show that this c is unique. To do that, we will use the Rolle's theorem. The Rolle's theorem says that if f is continuous on a closed interval a comma b and differentiable on the open interval a comma b, and if f of a equals f of b, then there exists a number x equals c in the interval a comma b such that f prime of c equals 0. We continue with the proof and assume that there are two distinct solutions. And so suppose there are two distinct solutions. And so we assume that the solution is not unique in this case. And we call this A and B. Then it must be the case that f of A equals 0 and f of B equals 0, because A and B are the solution, they are the zeros. Then f is continuous on the closed interval a comma b, and this function f is also differentiable on the open interval a comma b. What are a and b? A and b are the two zeros that we assume here. And then f of x is given x cubed plus 4x to the negative 2 plus 7. Then f prime of x is 3x squared minus 8x to the negative 3 plus 0. And this is 3x squared minus 8 over x cubed. If we factor out x squared, then we end up with 3 minus 8 over x to the 5th. Now remember that x is in the restricted domain from negative infinity to 0, so x is negative. If x is negative, then a over x to the 5th power is negative, and negative of a negative is a positive number. And so this factor is positive, x squared is always positive, f prime is always positive. But this is a contradiction, because if f prime is always positive, then there is no x equals c such that f prime of c equals 0, because f prime, we just showed that is always positive. There's no c such that the derivative is 0. And so this is a contradiction. Now, it is a contradiction because we assume that there exist two distinct solutions, and so our assumption must have been incorrect. And so this is the incorrect assumption. The only assumption we made was that there are two distinct solutions, and this assumption gives rise to a contradiction. And so this assumption is incorrect. Therefore, there exists only one solution. There cannot be two distinct solutions, and that finishes the problem.